right, we're doing action potential and we are starting now. Okay, so the last section of this lecture is the action potential. All right, so this is the one we've all been waiting for. So here we go. The action potential. All right, so this is the electrical activity that gets talked about the most in neuroscience, okay? And when people refer to it, they might sometimes call it, so this is sometimes called a nerve impulse. It can also be called a spike, okay? And an action potential can also be described as when a neuron fires, okay? When a neuron fires. All right, so what does this look like at the membrane? Let's make ourselves a nice big diagram. All right, so once again, ooh, wrong color. Okay, so once again, we have our cell membrane, the phospholipid bilayer, okay? All right. Here we go. So, once again, this is the outside, and this is the inside, okay? And we're going to diagram the entire process of an action potential starting at the resting potential, okay? So, let's start with when the neuron is at rest. We're going to start with a lot of sodium on the outside and potassium on the inside, okay? So we've got okay, so lots of sodium on the outside. There is a little bit of potassium out there, but the large majority of it is sodium, okay? So just a couple of potassium ions also outside the cell. Probably very soon to be pumped inside by our sodium-potassium pump, okay? And then on the inside of the cell, we have lots and lots of potassium, all right? We have a couple of sodium ions. Wait, let's do this in the proper order. All right. Then we do have a couple of sodium ions in here. Okay. Just a few, and they're probably soon going to get pumped out by our sodium-potassium pump. Okay. And actually, there is a third ion, which we mentioned before when we talked about the graded potentials, okay? So on the inside of the cell, there's also a couple of chloride ions, okay? So we didn't talk about them before, but here they are. So we'll add them to our list here. Chloride ions. Let's see what shape to give them. We'll give them a triangle. Let's give them the triangle. All right. So this is a chloride ion, okay? Lovely. So chloride. All right. So what this does is it makes the inside of the cell more negative than the outside of the cell, okay? So we've got more negative and the outside is more positive, okay? Great, so this is, as we said before, this is the resting state. Okay? So now, I'm gonna draw a line here to show that now, when we're moving this way, we are moving in time instead of in space, okay? So it's the same piece of membrane that I'm showing you in several stages over time, okay? So at this point, say that, like we saw during the graded potential, some kind of chemical interacts with the membrane of the cell and ions start to flow, okay? So then when the flow of ions across a chunk of membrane makes the inside of the cell a lot more positive, okay? So remember before, graded potentials, they were between 1 to 15 millivolts, okay? Now, if we go more than that, at least 15 to 25 millivolts, okay? So if the inside gets really, really positive, then we're finally going to talk about these gated channels when they are voltage gated, okay? So let's use this color. So in between this chunk and this chunk, what has happened? All right? Yeah, I can use blue. Okay, so this is when, yeah, let's keep using blue. Okay, so when the flow of ions across one chunk of membrane makes the inside of the cell much more positive, okay? And I said it was going to be greater than 15 to 25 millivolts. So the change in millivolts has to be really big, okay? This change in the electrical potential, it opens voltage gated in this case specifically the sodium channels, okay? Na+ channels. Okay, so remember what I said earlier about these gated channels. It requires something to act as a key to unlock them. In the case of a voltage gated channel, guess what the key is? The key is this change in voltage, okay? So voltage-gated channels. When the voltage changes, when the electrical potential changes enough, then channels will open. And remember, the sodium ions, there's so much of them outside. They're just looking for the opportunity to go into the cell, okay? So now this is their opportunity. Once these voltage-gated sodium channels open, there's a huge rush of sodium into the cell, and that is called depolarization. So what we're going to do is we're going to draw now. Okay, so we've got our voltage-gated sodium channel. Okay. It has opened up. It's now letting in tons and tons and tons of sodium into the cell. Okay. So many sodium ions are just rushing in. Okay? It's like, do you guys know about how in the US there's Black Friday? If you look on YouTube, they're just like totally insane videos of, you know, people waiting for the doors to open, and then the doors open and just everybody goes in like a flood. Okay, that's what's happening here. The sodium ions are flooding into the cell. All right. So this is and we still have all of our potassium ions. They're still in here. You know, they're still just hanging out. And we also still have a couple of chloride ions. So let's put the symbols around them. Okay, so nothing has changed except the sodium has rushed into the cell. So what does this do to the electrical potential? Okay, so it starts out positive, but then slowly the outside gets more and more negative as more and more sodium goes in here. And the inside starts out negative, but it gets more and more and more positive. And this state, we said, is called depolarization. Okay? All right. So, our next chunk of time. All right, so what happens in this next chunk of time? So eventually, these channels, they will become inactivated, okay? So during this time, as time passes, the structure of these channels change. And they change so that they're technically open, but they're blocked. Okay? So no more sodium can come in until this block is removed. Okay? And that's just something that you have to wait. There's nothing you can do. You just have to wait. All right? So in this next block of time, actually, let's make it a little more visible by using a different color. I'm sure you've noticed by now that I really like using colors. Okay, so this chunk of time. And now in this chunk of time, what happens? So, eventually, the outside keeps getting negative and negative and negative, but when the flow of ions, so when the flow outside at least 80 millivolts more negative than the inside makes the outside at least, so greater than 80 millivolts more negative than the outside. This change in the electrical potential then opens our other voltage-gated channel, the potassium channels. And now it's so positive and crowded inside the cell that the potassium's just like, get me out of here, okay? So the potassium's gonna rush out of the cell, okay? So when the flow of ions makes the outside of the cell at least 80 millivolts more negative, than the inside, okay? Yes, all right. So when the outside gets more negative than the inside, this opens voltage-gated potassium channels. And let's underline these. All right. And this lets a rush of potassium out of the cell, and this is called repolarization. I know, very, very creative names here. Okay, so let's draw our potassium voltage-gated channel. Okay. All right, so now potassium is loving this. They're just gonna all rush out and have a huge party outside of the cell. They're like, yes, we're finally out here. Okay, and there's, one in here still waiting in the queue to get out. Okay. Okay, so the potassium rushes out of the cell. And remember, we still have plenty of sodium in here. And we also have a couple of chloride ions. They're just chilling. Okay. All right. So this means what happens? The outside of the cell goes from being more negative to suddenly getting more and more and more positive. And the inside of the cell starts out being positive because of the depolarization. And then because it's losing all of the potassium ions, it goes negative again, okay? So this is called repolarization. Okay. All right, so then we have another time step. And during this time step, guess what happens? The potassium voltage-gated channels also get blocked, okay? So eventually, it goes, oh, okay, enough of you are outside. We're gonna block this gate now. Okay, so now neither of them can, these are both inactivated, the sodium and the potassium. So nothing can move through these channels where they can just really super fast go out for free, you know, because there's this pressure that the sodium wants to go in and the potassium wants to go out. So how do we rebalance this? Well, that's when our good friend, the sodium-potassium pump, does its job, okay? And it brings everything back into balance, or back to resting state, really. And actually, resting state is deliberately unbalanced. It's this state in biology called, what is it? Dynamic equilibrium. Is that the thing I'm thinking of? Anyways, it's deliberately kind of, you know, kept in this state of tension so that there's always a possibility to move, okay? If there's no movement, there's no life, all right? So you always need this possibility to move for there to be life. Okay, so our pump is now working hard to recreate the resting state, okay? And so this is just called back to resting potential. So now the outside once again is more positive than the inside, which is more negative. And this is called the return to resting state. Okay, couple of details. So when the potassium rushes out of the cell, sometimes so much of it rushes out that it actually, the inside becomes even more negative than it is at the resting state. That's called hyperpolarization, okay? And that's also something that can be fixed by the sodium-potassium pumps. Also, once this whole process happens, it still takes a while for the sodium and the potassium voltage-gated channels to become unblocked. So there's this period of time where nothing can happen really, and you're just waiting. You know, the pump is working and you're waiting for these voltage-gated channels to get unblocked. So this is called the refractory period. Okay, so after this, we enter, well, actually, it's kind of all in the same time chunk. So this is already the refractory period, okay? And right here, just before these channels, the potassium voltage-gated channels, just before they get inactivated, blocked, that's when hyperpolarization happens. Hyperpolarization. Okay? All right. Cool. So if we were to look at an axon with the myelin sheaths, here, let's draw that. So let's see, we have here our axon, and we've been drawing our myelin sheaths in green, so I'll continue that tradition. Okay, and maybe I just do this. I'm not going to draw a ton of them just because this is simply to demonstrate what this looks like going down an axon. Okay? So, the action potential, oh no, I'm foolish. Should not have done it in green because that's the color of one of our ions. Okay, sorry about that. We're going to redraw this real quick. Okay, so bam, 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 bam. What's a color that I don't use? Okay, we can use red because we're not gonna, the chloride ions aren't gonna be part of this drawing. Okay, so what happens? So first, sodium rushes in. Okay, sodium rushes in and it's going to spread out inside of the axon membrane. Okay, after sodium rushes in, potassium rushes out, and that also is going to spread out outside of the cell. This, it goes whoosh, whoosh, and then because all the sodium is in here, it's going to propagate past the myelin sheath, okay? And then you're going to get, once again, over here, whoosh, and then whoosh, okay? So sodium in, potassium out. And then the ions get all mixed up in here. They get changed around because they're all kind of mixing inside of the cell. And then over here, sodium channels open, sodium gets let in, potassium channels open, potassium gets let out. The sodium ions inside change the electrical potential over here and then over here, and that once again opens up the voltage gated sodium channels. Oops. And once again, we have a rush. We have a rush of sodiums in, and then a rush of potassium out. And then it just keeps propagating all the way down the axon like this, okay? So, like we did with the graded potential, I'm going to draw a graph, and this is probably what you'll see again in most textbooks when they're describing the action potential. Okay, so let's make a graph here. This is time. Okay, this is millivolts. Okay, so if we start at resting potential between 40 and 90 millivolts, so let's call it 70, minus 70, remember, because the inside is more negative. Okay, we're going to see, what color should I use? Okay, so if this is our resting potential, let me use blue. Okay, blue is our resting potential. Each cell has a threshold potential, okay? So you remember how I said here, I didn't give a specific number, I said a range, at least 15 to 25 millivolts more positive, okay? What that means is different cells, and remember we found out that there are many different kinds of cells in the nervous system. Different cells have different thresholds that open the voltage-gated channels, okay? So let's pretend that the cell that we are looking at, all right, so if we're at 70 and we wanted to, let's just say 30 millivolts more positive, okay? So our threshold is going to be minus 40, all right? So this is now our threshold. Okay, so this is resting state, and this is our threshold. So what the electrical potential is going to look like is, so first we're hanging out on resting state, and then something manages to push the inside of the cell much more positive, okay? And then we get a huge rush of sodium ions in. Then the sodium channels get inactivated. And a huge rush of potassium ions out. So it gets really negative, and sometimes it dips below the resting potential. And then the sodium-potassium pumps bring it back to rest, okay? So yeah, here we are. We're starting here. Some kind of stimulus, like a light, a chemical, or a vibration, or a signal from another cell, okay? So this is some kind of stimulus, okay? Stimulus just means like, you know, something that initiates an action, okay? So that causes that to bump up to the threshold, and as soon as it hits the threshold, all the sodium channels open up in this chunk of the membrane, and so we reach depolarization, okay? Then sodium channels get inactivated, and potassium rushes in, and we get repolarization. Oh my goodness, it's difficult to write sideways. Okay? Then this bump down here is the hyperpolarization. Okay? And then, depending on the cell, some part of this area, starting with the hyperpolarization, is the refractory period. Okay? All right. And I believe just got a couple more facts to tell you. Okay, so action potentials. Why do we need them? They're essential for cells to communicate quickly over long distances. All right? They are also what is called all or none. Okay, what does this mean? This means that until the electrical potential reaches this threshold, nothing's going to happen. If it doesn't quite reach the threshold, let me use another color. So say that this is another time, and it only got up to here. It's just going to go right back, okay? It's not going to do anything. It's not going to fire or spike, all right? But once it does reach the threshold, it always has this shape because of the biology or the physics, really, of what's happening here, okay? And that's why it's also called a spike, because it looks like this sharp spike, you know, going up and then down and then settling back again, okay? All right, so it only happens if the inside of the cell becomes positive enough to open the voltage-gated ion channels, and this is called reaching the threshold potential. And it always happens in more or less the same way, regardless of what triggered the action potential, okay? So the action potential, so firstly, it was one of the first electrical signals that we recorded from neurons. And because it has this all or nothing property, people thought, oh my goodness, that's kind of like binary. It's kind of like it's either on or it's off. It's 0 or 1, okay? So this also contributed to the metaphor that neurons are like computers, okay? But remember, neurons don't just use action potentials. Nervous system cells use all three: resting, graded, and action potentials. So this is another reason why they're not exactly computers, and the metaphor is useful, but it only takes you so far, all right? Okay, so next time, or the next video, we're going to talk about what happens when these potentials, so okay, all of these potentials, all of this electrical activity is happening inside of one cell, okay? It all happens within the cell. When the cell actually wants to talk to another cell, when it wants to pass something to another cell, that is all chemical. And there are two ways, or two connections that cells in the nervous system can have, and that's what we're going to talk about next.